Together with Mateusz, we'll be talking about deploying Airflow on GCP using autoscaling and what we have learned along the way. Some more details about us. My name is Anita Franczak. I'm a software engineer at Google. I am working on Cloud Composer.
And my name is Mateusz Hens. I have worked for Google for 4 years. Right now I'm working in Cloud Composer team as senior software engineer. And in the last couple of months, we together work on Airflow autoscaling in Cloud Composer. And today we would like to share our experience.
For those of you who have not heard of Cloud Composer, Composer is a cloud offering of open source Apache Airflow. It manages deployment and runtime of Airflow on GCP. Here's an agenda for our meeting. First, I'm going to run a short introduction into why one would like to implement autoscaling. Then Mateusz is going to take a deep dive into the actual implementation. So, why autoscaling? Before we can answer that question, we need to understand how the simplest working deployment without autoscaling works. Here's a topology of Composer's initial solution. The whole solution runs on Google Kubernetes engine. Both Airflow scheduler and worker run as Kubernetes pods. In the current deployment, we have one Kubernetes pod for running Airflow scheduler and user-defined number of pods for running Airflow workers. This deployment runs on a user-defined number of cloud compute machines. It is a good working solution, but it has its drawbacks. First, the number of nodes does not change with the traffic. Also, once you have chosen your machine size, you can no longer change it. In a current setup, you have one worker per node, so the number of Airflow workers is constant. What you are paying for are the cloud compute machines that you reserve for that setup. The cost is constant no matter the actual node usage. To address those issues, we have come up with the following solution. We have implemented horizontal autoscaling of worker pods, meaning number of workers automatically adjust to the load. We do not offer vertical autoscaling, meaning that worker resources requirements like CPU, memory, and disk do not change automatically. Mateusz will explain why later on. But we do offer the possibility to change worker resources manually after the environment has been created. We have not implemented autoscaling for Airflow Scheduler, but Airflow Scheduler parameters are separate from worker parameters and can also be changed after the environment has been created. To make all that work, we use GKE Cluster Autopilot. With this solution, user no longer manages cloud compute nodes, but only Kubernetes pod requirements. GKE Cluster Autopilot changes cost model from compute node-based to pod-based. With this model, you pay for your chosen minimum number of workers when there is no load, and for at most chosen maximum number of workers when there is load. You no longer care about bin packing of pods to nodes. Here's a simplified architecture for autoscaling solution. We still have one scheduler pod. Number of worker pod is dynamic and varies depending on task load, and this is controlled by horizontal pod autoscaler. Cluster is managed by GKE Autopilot. Mateusz will explain details later. This implementation supports well use cases like varying load during the day with a mix of small and medium tasks. It also supports use cases like a few batch jobs a day with no work to do in between. What it does not support well is big machine learning tasks requiring huge machine for a few hours. In this case, better use Kubernetes pod operator with a machine created specially to handle the task. A side note, Airflow is an orchestrating tool, not an ETL tool. Your data processing should be done in a different tool. If you have both small and huge tasks, you will have to size your pod to huge tasks. So during small tasks execution, your pods will be underutilized. This is how you configure Cloud Composer autoscaling. You can change machine settings for worker and scheduler separately. They can be changed after the environment has been created to better match your load. You can also set minimum workers to always have some capacity in case tasks come. To be able to cap the costs, you can use max number of workers setting. For now, both workers and schedulers cannot be scaled to 0. If you want to disable autoscaling, just set minimum workers equals maximum workers. Mateusz will now dive deeper into how we implemented this.
Okay, thank you, Anita. So let's take a deeper look. Kubernetes has a nice feature for resizing the number of pods. It's called horizontal pod autoscaling. It's a process running in GK master, so it's free of charge for the end user. It is metric based, so we need to provide it with a metric based on which HPA decides to scale up or scale down. By default, and I think the most commonly used metric is average CPU usage. It makes sense for example, web servers, but it won't be very useful for Airflow. But fortunately, HPA supports reading external metric from, for example, cloud monitoring. To design our metric, we ask ourselves a question. How many workers do we need right now to run all the tasks that we have? And to find this number, we need first takes the number of queued tasks and then worker concurrency setting. If we divide one by another and round it, we will get our value. For the metric, we also need to know how many workers we have right now. Having all of this, we can introduce a new metric and export it to cloud monitoring. Note that the HPA requires us to provide the values in scale factor format. So, for example, 1.0 means no change, 0.5 means take half of the current number of workers, and 3.0 means we need 3 times as many workers as we have currently. Okay, so with this metric, we are able to change the number of workers. However, we need to be able to run the additional pod somewhere. While Kubernetes schedules a pod in the node, it takes into account the pod CPU and memory request and looks for a node which has at least this amount of resources free. In Composer V1, we don't have resource requests defined, so Kubernetes uses the best effort resource allocation, meaning that if a pod wants additional memory and it is free in the node, then it gets it. This approach will not work with autoscaling. The infrastructure needs to scale up together with the number of workers that we have. And that's why we had to introduce worker scheduler size definition, CPU, memory, and storage, as user inputs. We also changed the type of the GK cluster that we use from standard to autopilot GKE, which automatically adjusts the number of nodes to the current needs. So if you want to have the full architecture of Airflow autoscaling in the Composer, then we could see this picture. The story begins in the scheduler, which put task in the task queue. From there, our monitoring component reads the size of the queue and exports scale factor metric to cloud monitoring. HPA is configured to read the external metric from cloud monitoring, and based on the value there, it resizes the number of workers. Everything is run on autopilot GKE cluster that provides infrastructure. The main problem that we tackled during the project was handling scaling down. So scaling up is easy. You just add a new worker, it is registered, and start executing tasks from a queue. There is a problem with scaling down. Some of the workers may still run tasks, and killing this worker means that the task is stopped and need to be retried by another worker. And this is, of course, unacceptable, as the task may be a 2 hours long and super expensive task, which after restart will abandon all current states and need to be started from scratch. Yeah, unfortunately, by default, the Kubernetes component that we used for controlling the number of workers picks just the number of workers to be removed. So we had to find a replacement for that. The problem was solved by replacing the existing deployment controller with a custom Kubernetes controller. So just a few information what actually Kubernetes controllers are. In Kubernetes, controllers are processes that are responsible for reconciling the state of the world, meaning like, for example, pods that are running in the cluster, according to the configuration. Like, for example, if configuration says that we need to have 3 pods of some kind, or we do it some template, but we have 4 of them, then the controller runs the code to remove one of them. It is registered in Kubernetes using a watcher pattern and executed every time something changed, either configuration or state of the world. Examples of controllers that ship together with Kubernetes are, for example, deployment controller, stateful set controller, or job controller. For our case, we implemented a custom Airflow worker set controller that replaces the existing deployment. It is now responsible for applying all the changes to workers. For example, for scaling up, it adds more workers. For upgrade, it replaces all the existing workers with the new one using the new version. During scale down, it connects to Airflow metadata database, gets a list of workers which don't run any tasks, and removes only workers from that list. Of course, it may happen that we end up with a higher number of workers than desired. It means that all of them are actually running a task. Then we just need to wait for the task to be finished. So we never remove a worker running a task. This makes sure that tasks are safe until they are done. One note, there is, of course, no transaction. So it is still possible that a worker started some task between the time we checked the database and we killed it. Yeah, but honestly, I was never able to encounter this situation during my tests. So it didn't cause any problems like failed task. I believe that the time window is too short, just a fraction of a second. So workers don't have much time to do it. Like, even if it starts a task, then probably it won't be able to make much progress for it. Okay, so this is what we have right now, but what next? One problem that we see currently is the delay between the tasks are added to the queue and the new worker started executing them. Like, there are multiple places we could fix it, but we believe that the lower hanging fruit is the delay between the metric value is exported to cloud monitoring and HPA is able to read it. We plan to replace cloud monitoring with a new service that is currently under development in Google. It is expected to make new values of the metric available for HPA instantly. Right now, we see the delay something around 1 minute. We could also work on some kind of predictive autoscaling, either manual, when user indicates the time they expect high load. So we could prepare a proper number of workers before, or even based on the history of tasks. The other idea that we have right now is scaling down to 0. So HPA does not support it out of the box. We would like to scale down not only number of workers, but also scheduler and other components to lower the costs of the idle environment as much as possible. This could be useful for users that run Composer environment occasionally, like once a week or even rarer. And that's all that we have for today. Thank you very much.